Good morning, class. Wait about one more minute and then I'll get started. Actually, I'm going to get started right now. See, I'm up to 15 people. So, hello and welcome. Hope everyone's doing well. Last time I wanted to just do one more problem of simplifying resistor networks to help you with the last quiz. And so let's just suppose we have a resistor network that looks like this, and what we want to do is we want to simplify it to a single resistor using the rules for series and parallel circuits. So this is an example from last time, and it's going to go through all of the equations that we learned last time. So what is the current that will flow out of the battery? So we learned about two different types of connections, okay? So there was series, and most often series looks like this. Two resistors, one after the other, okay? And so, but in general, the rule is two things are in series if you can go from resistor A to B without the wire forking. Okay, so if you can do that, for example, right here, these resistors are, I go this way and then I turn. So I can go from this resistor to that resistor without the wire breaking into two parts. Okay, the wire can turn, it just can't break into multiple parts. So these two are in series. And so we learned that R sub S is R1 plus R2. So I could combine those into a 15 ohm resistor because that is 10 plus 5. And then these two are also in series because I can connect them by that link right there. And so that would be 4 plus 15 is 19 ohms. So these two combine to make 19 ohms. So then what you do is you redraw the circuit. We have some food supervision. Hazel is supervising Bug eating his breakfast just to make sure that not a drop is spilt. So now what I'm going to do is I'm going to redraw the circuit, but with the pairs of resistors replaced with a single equivalent resistance. So I've replaced these two with a single 15 ohm resistor, and I've replaced these two with a single 19 ohm resistor. And then this is a 20 ohm resistor. Okay, so then we learned about parallel connections. And a parallel connection looks like a wire that forks, okay, then you have a resistor in each branch of the fork, and then it comes back together, okay? And so the formula for parallel resistors is a little bit more complicated. It's 1 over R sub P is equal to 1 over R1 plus 1 over R2 plus however many there are. So there's a really nice way visually to see if two resistors are in parallel. So basically, if you can do a loop in the circuit with only those two resistors, then they are in parallel. Okay? What's happening? Oh, it's hard to capture that. We had a doggy battle going on.
We had a doggy battle. We had a doggy battle.
Okay, so if I go around this loop right here, it has only these two resistors. Okay, so these two are in parallel. But here's the tricky one, and there's a resistor like this in the quiz from last time. This resistor is also in parallel with these two. All right, so how do I know that? If I go around this loop right here, see how this loop, I only pass through those two resistors. So the 20 and the 15 are in parallel because of that loop right there. And the 15 and the 19 are in parallel because of this big outer loop. So all three of these are in parallel. Okay? So I have 1 over R sub P is equal to 1 over 15 for that first one, plus 1 over 20 for the second one, plus 1 over 19 for the third one. Okay? Now, the biggest mistake that I observe students make is they do this sum, okay, which is equal to 0.169, but they forget that this is the formula for 1 over R sub P. So what you then have to do is then invert this number, so 1 over that, and I get that the equivalent resistance is 5.9 ohms. Okay. So now I redraw it with all three of these collapsed into a single resistor. So what you do is you just remove all of them but one. It doesn't matter which one you do. Just remove all of them but one and replace that one with the equivalent resistance size. All right. And so I would combine those to get, so those are then series because I can go from, they're not in parallel. So even though they're pointed in the same direction, these two resistors are not in parallel. Because if I do a loop that has both of these resistors, if I do a loop in the circuit, look, it also has to have the battery. So they're not alone in the loop. So the two things have to be alone in the loop for it to be considered parallel. All right, so we add those two together. We get R sub S equals 7 plus 5.9, which is going to be 12.9 ohms. Like that. So we have 18 volts and 12.9 ohms. Now, once you get it to just a single resistor and a single battery, we use Ohm's law. So Ohm's law says that the voltage equals current times resistance. So this is the voltage of the battery, and this is the total equivalent resistance of the circuit. Okay? So the voltage of the battery is 18. The current, or the resistance is 12.9. So I can divide by 12.9 and get 1.39 amps. Okay? So these were our main equations from the last lesson. The formula for series resistance, the formula for parallel resistance, and the formula for Ohm's law. And don't let me forget to give you guys the ohm puns once I'm done today. Okay, so today we are going to talk about the new topic for today is power, which I already talked about for about one lesson, but we're going to talk about power more formally today. And so we're going to start off by talking about power in general. Okay, so not applied to circuits specifically. And then we're going to apply power directly to electric circuits. Okay, so power is denoted by P. All right, and it is equal to the work done, or we could also think about it as the energy consumed divided by time. Okay, so in this case, if you have an object that is doing work, then that's like something that is outputting power. Okay, so outputting power would be, for example, a battery is going to output power. A solar panel is going to output power. Okay, meaning that it's doing work on its surroundings, transferring energy to its surroundings. For if something is consuming energy, then it is using power. So if something is using power, for example, a light bulb or your computer, and hopefully it's using that power to do something that is useful. So I like to just write the equation for power as energy divided by time. So some form of energy, whether it's work done or energy consumed or what have you. So this tells us that the units of power are units of energy divided by units of time. So that's going to be joules per second. All right, but that has a special name. It is called the watt, W. So 1 joule per second is equal to 1 watt. All right. So that is power. So there are a couple of different ways to calculate power. All right. So one way to calculate power is to look at the change in energy of the object. Okay, look at the change in energy of the object. So we'll do a couple of examples of how this would work. Okay. So let's suppose you have an elevator has mass, let's say 250 kilograms. It is lifted into the air. It is lifted let's say 13 meters into the air in, let's say, 3 seconds. All right. What was the power output of the elevator motor? Okay. So if we think about this elevator, the elevator starts out at y equals 0, and it ends up at y equals 13 meters. So it goes up this amount. So it gained gravitational potential energy. So what we're going to do is we're going to look at the change in energy of the elevator. So in other words, how much gravitational potential energy did it gain? Well, it gained mgy of gravitational potential energy. So that's the formula for gravitational potential energy. So we have m, which is 250, times g, which is 10, times the amount of elevation that it gained is 13. So that is a total amount of energy gained of 32,500 joules. Okay, so now power is the energy gained divided by the time it took to gain that energy. So it's the rate of consumption or the rate of output of energy. So now to get the power, we do energy gained divided by time. So 32,500 joules were gained in 3 seconds. Okay. So that is a power output of 10,833 joules per second, also known as watts. Okay. So, so what we did is we identified in this example that the form of energy that's being gained is gravitational potential, and so we use that as the numerator in the power equation. But we could have other situations too. So, for example, a car has mass 2,000 kilograms. Okay. The car, oh, excuse me. The engine of the car accelerates it from 0 meters per second to, let's say, I don't know, how about 25 meters per second in 4 seconds. Okay, what is the power output of the engine? So, in this problem, we have a car that is accelerating. So if you are accelerating, you are speeding up. You are speeding up. Okay? And so that means that you're gaining kinetic energy. So the car starts out with an initial kinetic energy of 0 because it starts out at rest. It starts out with 0 meters per second. And then it goes to some final amount of kinetic energy. Okay, so that's going to be 1/2 mv squared. So the mass of the car is 2,000. The speed of the car that the car accelerates to is 25. So I square that. And so this is going to be 625 times 1,000. So that's going to be 625,000 joules. Okay. So you can see that the car went from having 0 joules of kinetic energy to 62,500 joules of kinetic energy. Okay. So that means that the power is the energy gained by the car divided by the time it took. So it gained 625,000 joules of energy, and that took 4 seconds. And that gives us 156,000 watts is the power output of the engine. Let's convert that to horsepower. This is about 200 horsepower is the power. I'm not sure what the engine, so that's probably a high performance car if it's 200 horsepower. That seems like a lot to me. The power output of my parents' boat engines it had 2 engines at 250 horsepower each, so 500 horsepower. So that's a pretty big engine because boats are a lot heavier than cars. So, yeah. All right. So there is another way of calculating the power. Okay, and so that is calculating power using forces. Okay, so as I said before, power is the work that is done divided by the time it took. Okay, the formula for work is, and this is going way back to energy, we learned that work, which is a transfer of energy, is F parallel times the displacement, where the displacement is this way, all right, and let's say that here's the force that is applied. And so what we do is we take the force and we break it up into components. And one of the components is perpendicular to the displacement. The other one is parallel to the displacement. What is going on? There's just a lot of doggo activity today in this house. So that's from trigonometry. You get the F parallel. So we have F parallel times displacement. All right. And we divide that by the time elapsed. So what you see here is that we have displacement over time, which is the definition of velocity. So an alternative equation for power is F parallel times velocity. So we have F parallel times velocity is one formula for power. And then we could also think about it as energy gained per time. So there's multiple ways to calculate power. So let's do an example with using power in this form. Okay. So let's suppose you have a wall and there's a block, and you apply a force on the block. Let's say it's a 300 Newton force that you apply on that block, and that force makes an angle of 50 degrees with the horizontal, okay? And so as a result of that force, the block is moving upward, okay? So you're kind of like pushing the block up the wall, okay? So you're pushing, but because the block is pinned against the wall, it doesn't slide horizontally, it slides up the wall, okay? And so let's say that it's sliding up at 2 meters per second, all right? So what we want here is we want to figure out what is the power output of the person. All right, and so we're going to use the formula F parallel times velocity. So because the block is moving vertically, the parallel component of the force is going to be the vertical part of this force. So this is F parallel because the displacement is upward. Here the displacement was horizontal, so F parallel was the horizontal part of the force. But here the displacement is vertical, okay? And we can see that that is opposite the angle of 50 degrees that I've given you. Opposite, the trig function with opposite is sine. And so F parallel is going to be the total size of the force, 300, times the sine of 50 degrees. And that is 230 newtons. So now what we do is we then use the formula F, or power equals F parallel times velocity. So F parallel is 230. The velocity is 2 meters per second. So that gives us a power output of 460 watts. Okay. I'm going to show just like a fun application that I think is interesting. Okay. So this was the power output of a person at a particular instant. So your power can vary depending on how much force you're applying, how much effort you're exerting, okay? If you're exerting a lot of effort, you're outputting a lot of power. Okay? But your average power is pretty consistent, right? Because when you're sleeping, you're not doing any work, so you're not outputting any power. So we could actually estimate what is the average power of a human. What is the average power output of a human? Well, we know that the recommended diet for a person is about 2,000 calories per day. Okay? Now, calorie is a unit of energy, okay? And then day is a unit of time. So this is actually your average power output. Your average power output is 2,000 calories per day. And I say that only if you are not gaining or losing weight over time, because if you are consuming more food, so food contains energy, right? So if you're eating food and you're not using the energy in that food, then your body's going to store the energy and you'll gain weight. If you are eating food and you are using more than the energy contained in the food you ate, then your body is going to lose weight. All right? So assuming that your weight is staying constant, the energy that you're outputting every day is equal to the energy that you're consuming every day. All right? They're in balance with each other. If there's an imbalance, then you're either going to be gaining or losing weight. So this is the average power output of a typical human, but we have to convert it to watts. Okay? So it turns out that, so I'm going to do the railroad method of unit conversion. It turns out that 1 calorie is 4,200 joules. Okay? So if you eat 1 calorie, that's 4,200 joules of chemical potential energy that went into your body. And then 1 day is 86,400 seconds. So we can see that day cancels day, calorie cancels calorie, and I'm left with joules per second. And so what I get as the power output of a human it is about 97 watts, okay? Which is approximately the power consumed by an incandescent light bulb. So you are about, on average, you are as powerful as a light bulb. I think that's interesting. But remember, that's on average. There's part of the day where you're doing absolutely nothing, and so your power output is 0. So your power output can instantaneously be much more than that. So for example, if you're doing a pull-up or something like that, then your power output for that moment is going to be much higher than 100 watts. Okay, so we have just discussed power, so now let's connect it to electricity. What is electrical power? All right. So there's a formula for electrical power, and it is I times V. P equals I times V, where I is the current output and of the source, okay? And V is the voltage output of the source. All right, so that is electrical power. So we could take this and we could plug it into Ohm's law if we wanted to. And so we could get a couple of expressions. So if we took Ohm's law, V equals IR, we can also write it as I equals V over R. So if I wrote I as V over R, then I would get, and I plug that in for I here, I would get V squared over R. V squared over R. Or if I plugged V equals IR, and I plug that in for V, I would have I times IR, and I would get power equals I squared R. So these formulas are, this formula is usually used for the power output of the battery. And then these two formulas are kind of like the power consumed by a resistor. Okay. So I'm so tired today. Let's do some examples. All right. So what if I had just a really simple circuit like this? Okay. And let's just say this is a 12-volt battery. And this is a 2 ohm resistor, this is a 2 ohm resistor, this is a 2 ohm resistor. Okay? So, and I want to know what is the power output of the battery. All right? So in this case, what I would want to do is I would, again, simplify this entire network of resistors to a single resistor, okay? And then I would calculate the current, and then I would plug it into P equals IV. All right, so that's what we'll do. Now, the total resistance of this circuit, hopefully I can skip a step here. I can see that it's these two in series, and then once I combine those two in series, these two will be in parallel with the 2 ohm. So the total resistance is going to be 4 ohms in parallel with 2 ohms. So this is a shorthand way of writing that. And so if I work out what that is, I get 1.3 ohms. So all this together makes 1.3 ohms of resistance. Then I use Ohm's law. So I have 12 volts equals I times 1.3. And that says that the current is 9 amps. And then I have power equals current times voltage. All right. And the current is 9 amps. The voltage is 12 volts. And so that would be 108 watts is the power output of the battery. Okay. We will do one more example here. Suppose you have a battery, and let's say it's a 12-volt battery, and let's say it's connected to a single resistor that is a 2 ohm resistor. But this 2 ohm resistor is representing something else. It's representing an electric motor lifting a 1 kilogram mass. All right? It's an electric motor lifting a 1 kilogram mass. So the question is, how far is the mass lifted? In 3 seconds. Well, first of all, I better figure out the power, okay? So basically the power dissipated by the resistor is going to be equal to the power, because the resistor is a motor. So whatever power the motor is consuming is going to go into the gravitational potential energy of the mass. Okay, so so basically we have a transfer of energy here. We have a battery chemical potential energy becomes electric current, which becomes dissipated by the motor, or I guess used by the motor to turn it into gravitational potential energy. So the resistor's power is going to be the power of the mass. All right. Now the resistor's power is V squared over R from this equation right here. The mass is gaining gravitational potential energy, mgy, and in a certain amount of time. So that's the power consumed by the mass that's being lifted. So now what I do, and I'm trying to solve for y because it asks how far is the mass lifted. So I have plugging in numbers. I have V is 12, resistance is 2, equals M, which is 1, G is 10, Y over the time is 3 seconds. 12 squared is 144. Divided by 2 is 72. 72 times 3 is 216. 216 divided by 10 is 21.6 meters. Is the amount that this motor could lift the mass. Let me just double check the math on that. Yeah. Okay. So we can connect electrical power to other forms of power. So I will see you in the Zoom room. That's my